lab we're going to be doing is the aspirator lab, which is very dependent on flow rate and pressure. So I think it's important that you know a couple features about the building you'll be doing it in. When you're doing your lab, you want the water flow coming out of a faucet to have a constant pressure and a constant flow rate. When you're at some place like your house, if you have too much water running at the same time, it affects the system. But here at Rowan Hall, we have a very big pump that kicks in and provides the pressure to the water that you need to get good results in your laboratory.
Unfortunately, we were unable to get into the room that houses the first floor pump, which supplies the pressure throughout Rowan Hall to every single sink, every single bathroom, all the places. Now, it keeps a constant 70 psi pressure taken from this picture of its gauge. Now, it is always supposed to be at 70 psi. Not supposed to be higher though, but you should check it just to see if there's an anomaly or there's a problem. And also, there's a high chance of you not being able to get access to this room, as very little people have a key to it, and it's almost random when it's unlocked or locked. And also, the 70 psi does not go directly to sink. As you know from Bernoulli's, there's going to be a high pressure drop as water travels up in altitude, as going from the first floor to the third floor, that's a 20-something meter increase in height, and change the pressure to as low as 40 psi once you get to the sink.
When you're using the aspirator, you can't just do something like assume a perfect Bernoulli's relationship, because if you take a look at this cross-sectional cutout, there's changes in the diameter all throughout its structure. That's going to change your flow.
Now here's a model of the aspirator, and it includes the inlet ports, which is here, and then the outlet. This inlet port is for suction. This one is directly connected to the faucet. Now the water travels from the faucet down through the aspirator, going from 10.75 millimeters to 2.7 millimeters right here, which sort of acts as an orifice in getting a smaller diameter, and then it travels down to here, which also in diameter becomes 5 millimeters, creating a pressure of a area of lower pressure, creating suction coming from this inlet, which is the vacuum inlet, which includes this blue stopper right here. Well, it's going to be red in the aspirator, and it tilts in a certain way that allows stuff to come in but not go out. And that has a small internal diameter of 0.889 millimeters, which is extremely small, comparing it to this diameter, which is 2.7 millimeters, which is 1/3. And then it travels in, the two streams meet together at this point, and then travel down and out the aspirator.
Also in this cutout, there's some pieces missing, like a blue orifice where the faucet water initially goes in. You're going to need to be able to measure the diameter of this, and there's many different methods. One of it is to use a setup like this, piece of metal tape wrapped around it, and push it into a point where it stops, and you can just measure your tape thickness, and that'll get you your diameter.
In your textbook by Noel D. Nevers on fluid mechanics, there's an example that actually relates to the aspirator laboratory. Now, if you go to page 262, there's going to be an example with a Bunsen burner with gas coming in and out there, and then and is sucking in air following the same path but from this direction in and then out, where they combine in a combustion reaction producing the flame. Now you can relate this to the aspirator lab with the faucet water in this direction going up, and then the suction water coming from here. And then in the example, they derive equations relating the pressure over here, but there is a problem as they messed up the signs for the velocities. It should be velocity of air 2 minus V3 in these equations. And if you switch the velocities, you will get a proper calculation, but you have to do the derivation yourself and relate it to the aspirator. But this is a nice start for the calculations and should tell you if you're going the right direction.
Right now, no water is flowing through the aspirator, so we're at 0 psi. But as soon as you start getting a flow, the pressure is going to go up. As you can see, you've got some suction from that. Unfortunately, you have to wait a while for the water to come out of the aspirator once you actually turn the faucet off. This has an application using the suction to move around fluid. Over here, we have the aspirator turned off and fluid on this tube. Because of that, the fluid level's at a constant height because nothing's happening to the system right now. Once you start putting flow through the aspirator and getting suction pressure though, there's going to start to be a difference in the water levels. Remember that pressure can be related to rho GH, so by measuring the difference between these two levels when you have a flow going, you then have the suction pressure for that flow rate.
For the second experiment, you're going to be measuring the flow rate of the suction, which you're going to have to measure 4 things in this experiment. And the first one is the amount of water that comes through the aspirator from suction, which you're going to have a graduated cylinder filled with water, and you're going to mark the place where the water level reaches, and then in beginning, and then at the end, so you know how much water flowed through the aspirator from a hose that you're going to dip into the graduated cylinder below the water level. Then you have another hose connected to the bottom of the aspirator, which is going to go into graduated cylinder so you know how much water flows out of the aspirator. You're going to have a volume in the graduated cylinder as you're going to start from empty, which will be the water that flows out. Then you're going to have to record the amount of time that experiment takes place so you can get the flow rate of the water coming through and through suction and out. And with that, you can find the amount of water coming into the aspirator from the faucet. And then the final thing you're going to have to measure is the pressure gauge. Right here, it's going to give you the pressure in psi-G most likely, and you're going to use that to compare with your findings on what the pressure of the water is.
What you get when you're flowing water through the aspirator and you're also sucking water with the suction pressure is a modified flow rate, because not only do you have what's coming from the sink, you also have the water that you're sucking up coming out. This is the point of the second experiment of the lab, to see this relationship. So what you have are 2 graduated cylinders and a flow at a known flow rate. At the same time, you put this into the empty graduated cylinder, you put the suction tube into the filled one. So, in 3, 2, 1. Stop. What you have here is this graduated cylinder filled up with water, and this one having some water taken out. And you have a time for that to happen. Meaning, you know the flow rate coming out of here, and you know the flow rate from the suction, which also lets you find the flow rate coming out of the faucet. Out the building you'll be doing it in. So follow me to the service corridor. This is where we keep everything that's ever broken in the engineering building, which is everything. We have garbage cans full of sand, we have wooden planks, We have that. I don't even know what this is. There's a really big, scary saw blade, and I kind of want to touch it, but I'm not going to. Got some broken computers here. I say just run a magnet over them and smash them up. I don't want them anymore. But most importantly, over here, we have pump room, which is sealed tight. When you're doing your lab, you want the water flow coming out of the faucet